our morning session. It's my pleasure to introduce Adam Epstein, who will talk about transversality principles in holomorphic dynamics.
Okay, so I want to thank the organizers for inviting me to Russia. I've been here before. Or anywhere close, really. All right, so I want to say some words about some properties of very general properties of very general parameter spaces. And I just sort of usually collect these properties under the term transversality. I'll explain what some of these are. And I want to outline a unified way to establish properties such as these. So some background. So we could be looking at the space. These are really questions about moduli space, but oftentimes we might choose particular families, normal forms, and work in some parameter space. So the parameter space of all degree D rational maps is it's a smooth affine algebraic variety of dimension 2D plus 1. So in some sense, it's not very difficult to understand. We have explicit coordinates for it. We know its dimension. Of course, we're really interested in properties up to Mobius conjugacies, so there's a quotient operation. So we lose 3 dimensions in this, and it introduces some very mild singularities, which for our purposes today will be irrelevant. And what are the things you can talk about in one of these parameter spaces, or in one of these moduli spaces? So, of course, because we have explicit algebraic coordinates, you can just write down equations and ask about things, but we're doing dynamics, so you want to ask dynamically significant things. So typically, if you had a particular concrete family, maybe you're choosing a family where you're interested in following critical points or fixed points. So this might even be a family with labeled critical points or labeled fixed points. And if you have enough labeling, or at least if you have the appropriate local labelings, you can ask and write down various conditions, at least in principle, for various local properties of interest. For example, you might have some family of maps. This could be quadratic rational maps, but this could just be a partial specification in some more complicated setting where you have 2 critical points and perhaps one or both of these critical points is involved in the critical orbit relation. So here, this particular critical point is pre-periodic with given data, and this one is periodic. And if you had a reasonably explicit family, you could actually write down what this condition means in terms of the ambient coordinates and what this condition means. And these are clearly algebraic conditions that you're imposing. So after doing some symbolic manipulation, at least you'll have some polynomial equations in the parameters, one for one, and the vanishing of these polynomials. One of these will correspond to this condition being satisfied, the other to this condition being satisfied, and then you can ask about simultaneous solutions and so forth. You could also have there are other ways you get a critical orbit relations. You could have critical orbits merging, for example. You could have several critical points doing their own things, and then perhaps coming together, and then maybe some other critical point being periodic or pre-periodic and so on. And you can try to decompose this. Then it's not necessarily so clear that you can decompose such a setting specifically into this relation and this relation and this relation. There's really somehow a whole ideals worth of relations, and you could wonder about generators for it. But you can ask various conditions, like what are the loci cut out by the individual conditions? Or by some ideal of such conditions. Are these loci smooth? What dimension are they? What are their intersections like? Are they transverse? Are there singularities? Are there multiplicities? Right? And actually, especially if you have critical orbits merging, the answers that you get can actually be sensitive to the way you write things down. So part of the discussion here, when I will say that loci with critical orbit relations are transverse, there is an issue of how you define these relations when things are coupled. But the theory itself somehow gives you a preferred one when I get to that. So, okay, so one possible feature you could be interested in is critical orbit relations and also the breaking of critical orbit relations. Maybe I decide to erase that arrow, and now all of a sudden I have one critical orbit relation here, and some locus where this does whatever it does. What does that look like? Another consideration would be multipliers of periodic points. So if I have a periodic cycle whose multiplier is not equal to 1, then no matter what parameter space you have, you can locally follow this by the inverse function theorem. There's a unique nearby cycle, which varies holomorphically in the family, and so its multiplier is a local holomorphic function. And if you have several cycles, you could ask about a loci in parameter space where these multipliers do or do not change. And again, in principle, it seems like for each cycle you choose, the condition of fixing the multiplier should cut out a hypersurface. Maybe these hypersurfaces should be smooth. Presumably, if I take two different cycles, they should be transverse. Okay, well here it turns out that it actually matters, or it can matter, and what ends up being important is that the cycles be non-repelling, right? So it's actually not too hard to write down just algebraically isolated violations of transversality involving repelling multipliers. In the case where the multiplier is a root of unity, there are additional things you could ask about because these parabolic points have additional invariance. There's a degeneracy invariant involved. So you could have a family of maps where they all have a parabolic fixed point with the same multiplier, but depending on whether this parameter epsilon is 0 or not, the multiplicity is degeneracy, however you would measure that. Either you have a non-degenerate parabolic, a z plus z squared type situation, or you have a z plus z cubed type situation. So this is reflected in the number of paddles you see dynamically. So this is a family I've written down, but suppose you're working in any family or any well-presented family, you might want to make assertions about the, for example, the multiple. I'll make that too precise. There are things that you can write down. I'll illustrate in the picture. And also, in connection with parabolics, there's a quantity called the holomorphic index, which is some sort of not quite multiplier, but some additional continuous invariant. And you can again ask whether or not this quantity changes or doesn't change within the given family, or look at the locus where it changes or doesn't change, and ask, can you give universal conditions under which that quantity's variation cuts out a smooth manifold. That quantity's constancy cuts out a smooth manifold. Finally, if you want to get really ambitious, you can try to formulate something about Hermann rings, which I won't bother to do here because that's just a whole extra order of difficulty. But you can ask about the question, suppose you have a map with Hermann rings, what does the locus of maps with nearby Hermann rings of the same type look like? Is it a smooth manifold? What is its codimension? Suppose I have another Hermann ring somewhere else. Are these subloci transverse in any appropriate sense, and so on. Okay, so this is a host of different questions. They're all in the same spirit, but a priori they're about different things. And various questions in these categories have been addressed, many of them going a long way back, oftentimes with techniques such as quasi-conformal surgery. So particularly if you're interested in varying multipliers of attracting cycles, then this goes all the way back to the work of Sullivan and McMullen and Duody Hubbard and so on and so forth, where by explicit quasi-conformal surgeries, you can often prove that the multiplier map in a given situation with attracting multipliers has a local inverse and get transversality results that way. And somehow similar in spirit but more ambitious was what Shishikura did in his important paper on quasi-conformal surgery, where he showed not only that he gave a quasi-conformal deformation theory, not just changing one attracting multiplier to another, but actually starting with indifferent cycles and showing that you could construct a surgery to make appropriate multipliers attracting. So sometimes results like that, sometimes constructions like that can be used to infer transversality statements. I'm actually taking the opposite point of view. So the way I'm approaching, in fact, the actual historical origin of what I'm doing is that I was trying to study such surgeries, but trying to study them in a parametric context and then study them variationally. So for example, taking Shishikura's argument where he constructs small quasi-conformal perturbations to change the multiplier, trying to see if you could realize that in a smooth one parameter way, and then see what the derivative of that would look like. And then somehow, by contemplation of this process, somehow the original surgeries become less and less relevant, and this transversality, in some sense, is a way of inferring the existence of certain surgeries without actually doing them by hand, or more or less, inferring the consequences of certain surgeries by some general argumentation plus the inverse function theorem. Okay, so that's the spirit. So I should actually illustrate this with some concrete examples of things. So, just as an illustration of some transversality assertions, this is a slice, a parameter slice for quadratic rational maps, the moduli space of quadratic rational maps. Here I have labeled the critical points. And this is the slice for the Kanishanti. This is the slice pier 1 e to the 2 pi I over 10. So this is where you have some fixed point whose multiplier is this root of unity. And what are the things we observe about this slice? Well, one thing you can observe completely by hand, and this is contained in Milner's paper from more than 20 years ago, is that these slices here, in fact, pier 1 of anything, well, this is slightly more complicated what he's doing because he was doing the critically unmarked case. But up to squaring some parameter you can infer from what he's doing. So these are complex lines. In fact, there's a p over q is 1/10 here. I'm going to put the parabolic fixed point at infinity for right. So here's the all right. So f sub a, maybe I should say f sub a of z. If you want a normal form for this slice, there it is, with p over q being 1/10. And within this parameterization, you see various things. You see there are obviously, well, this is a little bit crude here, but this you're supposed to recognize this as a distorted copy of the main body of the main cardio of the Mandel set with one point stretched out to infinity. And here's the cusp. And notice the rest of this appears to be a smooth curve. Well, it is a smooth curve, but it's a regular curve. It has no singularities, no kinks in it. The same with all of these components attached. Those are non-singular real algebraic curves. So those are visible. Those are visible properties here, which are transversality assertions that actually is the situation. Let's see, another thing, this is a little bit hard to see, but here there are these, there's a collection of, I think, 8, there should be 8 of these, at least in the full picture, of these crossings here where you have crossing lemnis gates. So there are the white lemnis gates, whose boundaries that is in the bifurcation locus, and which are the root components of Mandelbrot type configurations here. And then going across these in the other direction, there are these shaded gray lemnis gates, which you may not be able to see. Yeah, and it's not the best contrast here. So, but one reason why you're not supposed to see them is that the boundaries of these have no topological there's no topological dynamical significance of the boundary. Each of these lobes of the lemnis gate is in one of these relatively hyperbolic components. And it just happens that there's something about these that's different from these analytically, namely that the holomorphic index, so there's always a parabolic point at infinity, and this point has an invariant called the holomorphic index, which will be some complex number, and there's actually some better way to measure this quantity, some affine rescaling of that quantity, so that what's depicted here is the locus where the real part of that quantity is positive, or actually non-negative, including the boundary there. And, well, for example, the fact that these do not cross, the fact that this index gives a conformal isomorphism from the appropriate half plane from an appropriate half plane in C to this lobe here, as opposed to having ramification points, which might, for example, end up linking two copies like that. That's an instance of one of these transversality assertions, one of the more subtle ones involving parabolics. Another is that at these crossing points here, that I just have the white lemniscate crossing the shaded lemniscate, as opposed to two white lemniscates with two interleaved shaded lemniscates. That's a transversality property about the degeneracy order, the thing related to what I was running on up here. So, and there won't be any Hermann rings in this family, so there's nothing like that. In terms of critical orbit relations, that's a little bit harder to illustrate here, but there are ways to see, there would be ways to recognize a violation. Okay, so the approach that I want to take to these is that since transversality has, I mean, there are various ways to define transversality, but the way I learned when I took differential topology is that it had an infinitesimal definition in terms of derivatives and tangent spaces. So that's the approach I want to take. And so, I mean, this sort of approach goes back quite a ways in and out of Teichmuller theory, but there's a nice explicit formulation of this in rather high generality. So, deformation theory for compact complex manifolds of arbitrary dimension in the work of Kodaira Spencer. And the idea is to just go back and think of what does it mean to put a complex structure on a topological manifold. And I'll draw here, I suppose, will be a Riemann surface because that's the most dimensions I can fake on the blackboard. But maybe I have a fixed, in fact, it might be better to think of this as a fixed compact differentiable manifold. And so a complex structure is given by a maximal atlas of charge with holomorphic overlaps. So you would imagine covering this manifold with a bunch of open sets, each which can be given some, each coming with some homomorphism to C, such that the overlap maps are holomorphic. And now what would it mean to vary the complex structure on such an object? So if you have a one-parameter family given in some way, maybe you have some equation whose fibers are complex manifolds of a given type. So if you have a one-parameter family, you can imagine varying, seeing the variation of the complex structure by seeing how the individual charts move as you move in your parameter space. And then seeing how the overlaps vary, and seeing whether the variation of these overlaps is somehow trivial or not. In other words, whether or not it's just induced by a global biholomorphism, or whether things change. So when this is all written down, when they wrote it down, it took on a very, very nice formulation in terms of cohomology. And essentially, the main thing that you compute comes out of taking very seriously this matter of overlap maps, and in particular looking what happens when you have three charts that could overlap, and comparing the overlaps and the overlaps and the overlaps, and taking the derivative of such a relation. So if this HUV, which is like HUV comma T, where T is your parameter, right? You have a one-parameter family of relations like this between overlap maps, and if you take the derivative of that, you get some relation between the derivatives of these quantities, and algebraically that takes the form of a one cocycle in a certain sheaf, the sheaf of holomorphic vector fields. Okay, and all sorts of things come out of that interpretation, and come out of this computation, the fact that it has a cohomological formulation. Okay, so that's one of the tools, and the other tool is going to be maybe more familiar, but so this is also related to Teichmuller theory. This is Thurston's work, Thurston's theorem in particular, and actually the rigidity case, the rigidity aspect of Thurston's theorem, which is probably the easier part, at least for me. Anyway, so these are, I'm going to show what this means. These are slides from a different presentation where I was talking about how once you do this theory, it makes sense more generally. So this is just to say what it is. Henceforth, whenever you see an F, you may as well just assume it's a rational map. But actually, nothing I say here will really depend on that in a serious way. F could be something in the exponential family, or the tangent family, or the Weierstrass P function, or appropriate family cooked out of the elliptic modular function, and the conditions that I need to set up the theory are here. Okay, so it's what I call a finite type map, and I'll just draw a picture of what the typical one looks like, or what a typical one might look like. So this is happening on some, doesn't even have to be on one Riemann surface. Maybe I have some finite union of Riemann surfaces. And some domain, which probably, at least if I have higher genus Riemann surfaces, almost surely is not the whole Riemann surface, but some open subset of it. There's a little bit hand-wavy here, but there are plenty of maps that look just like this. I could, if I wanted to specify particular covers, if I had a particular genus 2 Riemann surface here, I could say take its take a universal cover, and then from the disk, and then conformally embed that disk in this Riemann surface, and take that map, and maybe do something similar here, maybe introducing a few branch points and so on, and that would specify one of these finite type maps. Okay, and what makes them finite, well, aside from the fact that we have a finite union of compact Riemann surfaces, what makes the really key condition is that the set of singular values is finite. So singular value is a property of in a range, and these singular values are the critical values, the images of the critical points. Okay, in other words, points that have preimages where the derivative vanishes, and also the asymptotic values, points like 0 or infinity for the exponential family. So as long as that set is finite, and that's an extremely restrictive condition, as long as that set's finite, this theory will apply. Now, if you're working with something like entire maps, and you just write things down, you almost surely will violate this condition in a very, very serious way. So this is a somewhat sparse collection of maps, but it's broad in the sense that they exist in all sorts of Riemann surfaces, and I have no actual restrictions on the domain here. Okay, or if you like, just think of rational maps on the Riemann sphere. Okay, now this theory is a sub-theory of type-Euler theory, so I do need to say some words there, but if I'm restricting to rational maps, then the X here is just the Riemann sphere, and we only have to look at this line here. Okay, so the type-Euler space of, say, a compact surface with finitely many punctures, this is the space of equivalence classes of complex structures where the appropriate equivalence relation identifies structures related by pullback by an appropriate homeomorphism, the one which is isotopic to the identity preserving the marking. Okay, so that's a mouthful. If you are working on the Riemann sphere with a finite collection of points, you can sort of talk your way around this with a more concrete presentation of it. You end up paying somewhere else, but you can bury those details, you know, in a citation to classical papers in type-Euler theory. So you could take as a definition, if you wanted to, so suppose I have some set E that has n points. Most people will just write the type-Euler space of this sphere with n punctures and not label the punctures. There's a base point here that you can remove that a little bit. So there's something called the moduli space, or at least what I'll call a moduli space, where you preserve the labeling. This would be, so if I have n points on the Riemann sphere, the configuration space of n points on the Riemann sphere is just the product of that many copies of the Riemann sphere. But I would like these to be n pairwise distinct points on the Riemann sphere, so there are various diagonals and subdiagonals and so on and so forth that you throw away. And then finally, you want that up to global Mobius conjugacy. So one way to achieve this is to just declare that the first 3 points should be 0, 1, infinity, and then work in the appropriate product C to the n minus 3, throwing away various diagonals. So there's some very, very explicit space here with nice coordinates on it. And it's not simply connected, but it's a manifold, it has a universal cover, and you could declare its universal cover to be the appropriate Teichmüller space. Okay, and that's maybe not my favorite way of defining it, but you wouldn't be so wrong. Okay, so locally speaking, the local structure of Teichmüller space, which is actually all I'm really going to use, is that it just is locally like the moduli space, so that subject to some appropriate normalization of 3 points, I could be talking about this in coordinates extracted from the positions of the other critical values, for example. Well, from the other points, for example. Okay, so part of the formal background of Teichmüller theory is that there are conceptual a priori descriptions of the tangent and cotangent spaces in terms of cohomology. This is entirely in the same vein as the Kodaira-Spencer theory. This is a subset of that, really. And one doesn't have to say the word cohomology. In fact, usually one doesn't. Usually one does this in terms of Beltrami differentials in the tangent space. But then that brings in various analytical difficulties or various analytical issues that actually are sometimes harder than the material here. Everything I'm talking about here really wants to be algebraic, even though at the moment we don't have any purely algebraic way of doing it, but these are algebraic questions. Whereas solving the Beltrami equation, at least if you take the most general theorems, this involves words like measurability almost everywhere. There's a PDE. Right? So one way to avoid that or hide that, depending on your point of view, is to phrase things in terms of cohomology. So the tangent space, the Teichmüller space, is a certain first cohomology group, okay, where it's basically first cohomology in sheaf of holomorphic vector fields requiring zeros in appropriate places, namely along that set of points. What does this mean? That's very, very fancy terminology. What this means, so what is a tangent vector in configuration space, first of all? If my configuration space consists of n tuples of my points, a one-parameter family of these just involves moving these points separately, and then if I take the derivative of that, that just gives me a collection of tangent vectors to the Riemann sphere, one at each of these points. So a tangent vector to the configuration space is just an appropriate tuple, an n tuple of these tangent vectors. That's the configuration space, but I'm interested in the moduli space, or the Teichmüller space, but locally these are the same thing, right? So I can get at that by taking any 3 of these, for example, and just deciding to fix those points, and then measure the variation in the family, and then just take tangent vectors at the remaining points. Of course, somebody else tomorrow could have written down a different system of coordinates where they choose to fix a different triple of points, and then their tangents, then their variations would be 0 at those points, and have tangent vectors sticking out of the other points. So really, what's going on is there's a quotient discussion going on here. There's a notion of a trivial infinitesimal deformation, one that would be induced by a one-parameter family of global conformal maps. A one-parameter family of Mobius transformations, which moves this whole set E along in the same way, as opposed to somehow decoupled independent motions. So when you write this down as a quotient space, that turns out to be one of the standard descriptions of this first cohomology. Okay, and then for general reasons, which can again be seen on the level of Beltrami differentials, if you like, the dual to that space is an appropriate space of global meromorphic quadratic differentials, those allowing simple poles along that finite set. And the pairing that shows that these are dual is just the canonical pairing involving the residue sum that you would get when you write down an element of H1 of this and an element of H0 of that. So the point is that this is just pre-existing structure that's in the background, that's been there forever, that's embedded in the first chapters of all sorts of books and papers going back 50, 60 years. Okay, so this is, I sort of mumbled something about this. There are various presentations. One of the virtues of cohomology is that it has all sorts of presentations You can do things from an algebraic point of view or an analytic point of view. And if you're doing things from an analytic point of view, you usually introduce Beltrami differentials. And there's a description of the tangent space in terms of Beltrami differentials modulo so-called infinitesimally trivial, really infinitesimal Beltrami differentials, infinitesimally trivial Beltrami differentials. And one description of those, again, there are many, but one description of the trivial ones is that these are the Beltrami differentials which arise as d bar of appropriate vector fields. Okay, so this is getting back to the original heuristic of trying to vary things by changing coordinates or changing a map somehow by a small perturbation given by a vector field, but somehow doing this separately in various places and trying to see whether or not these individual deformations can be stitched together. Okay, if you take the analytic description, then this pairing, which could be given by residues, it can also be given by an integral. If I have a quadratic differential of the appropriate type, well, if I have a quadratic differential and a Beltrami differential, then I can write down that integral that has a meaning that's integrating a 1-1 form. And the 1-1 forms you get will in fact be integrable 1-1 forms. We'll get a finite well-defined number out of it, and that is the residue pairing, up to 2 pi I. So again, this is the Dolbeault isomorphism. It's a very, very special case of the Dolbeault isomorphism. Again, ideas going back at least 60 years. Okay, so what is a quadratic differential? So this is this abstract, this general notation in terms of cohomology, but again, you can write all these things down by hand in one complex variable. These are just tensors of a certain type. So if you have a Riemann surface and a quantity on the Riemann surface, which in the coordinate, so I'm using sort of old-fashioned notation I don't really like here, but we all do it when we do computations. So a quantity which in a given coordinate system you would express this way, where that phrase itself is just a shorthand for a bureaucratic procedure of how you're supposed to know how to change coordinates. Okay, so if you want to define a function, suppose you want to define a function on a Riemann surface, and you have the Riemann surface presented in terms of a bunch of charts and overlap maps, then I could give you a function. You could specify a function by for each of these coordinate neighborhoods specify a function. So here I have say coordinate neighborhood, coordinate chart alpha and coordinate chart beta, u alpha and u beta, and an overlap map. Okay, so really what I should be doing is, if I wanted to take seriously what I did before, then I would specify a function here by first covering with coordinate charts, actually taking coordinates into C, and then on these open sets in C, specifying some functions, I might call H alpha. And for these to fit together as a function on this Riemann surface, that implies a certain transition rule between what H alpha should be and H beta should be on this overlap. And to get a function, it should be that the functions here on this overlap differ, the descriptions differ precisely by a precomposition with this change of coordinates, as you'd expect. Okay, but suppose the next day you want to specify a vector field on a Riemann surface, and you go about the same procedure of choosing coordinate charts. Once you choose coordinates, you could pretend that a vector field is given by a function locally. You could specify a function here and a function here, but then of course you have to make sure you change variables in the appropriate way, and it should be the precomposition times, or in fact divided by, the derivative of the coordinate change. Okay, so for quadratic differentials it's just like that, except the multiplicative factor in the automorphy relation is the square of the change of variables. That's if you want a local description. Okay, so in important observation, well, all right, there's a couple important observations, but what I need to do is tell you where, so this description of transversality principles in the beginning may have seemed a little bit metaphorical or metaphysical. I am saying principle rather than theorem. If I want to get theorems where I can actually make a statement without having to qualify it by saying that I'm in this or that normal form that I've checked, then what I want to do is pose these in the right place. So my point of view is that you should prove transversality not in this or that space of rational maps or this or that space of transcendental maps, which you may not even have a priori, but in a space that somehow defines itself out of the structure involved, namely what I call the deformation space. But to define that, you need a little bit of Teichmuller theory. So this is a little bit abstract here, but essentially, if I have two subsets, let's say two subsets of the Riemann sphere, I can look at the Teichmuller space of the Riemann sphere marked at the larger set versus marked at the smaller set, and then forgetting the extra points from the larger set induces a map between these Teichmuller spaces, and these maps are holomorphic. They're well enough, I mean, all the aspects I'll talk about here are well understood. We know what their derivatives are in terms of that description, what their co-derivatives are. In fact, the co-derivative, namely the derivative on the cotangent spaces. The cotangent spaces, I said, were these spaces of quadratic differentials. Here, allowing simple poles along the set A, and here along the larger set B. And there's an obvious map between those, namely the inclusion, and guess what? Miracle of miracles, this is in fact the co-derivative of that forgetful map. Okay, bringing in, actually not even dynamics yet, but suppose I have a finite type map from one Riemann surface to another, maybe not yet dynamical. There's a fairly straightforward condition in terms of the covering space theory for when there's an induced map on the level of complex, well, there's always an induced map on the level of complex structures, but the question could be whether or not this map is compatible with the implied equivalence relations defined in the Teichmuller space. So when the appropriate conditions are satisfied, namely when the image of the set A is contained in the set B, and also when the set of singular values is contained in the set B, then you can do that. You get a pullback map. All right, again, really what's involved, if I have a surface here with charts here, I can imagine trying to pull the charts back to this surface here, and that's essentially what this map is doing. It's just doing this on the quotient level of Teichmuller space when that's well defined. Okay, and this sort of a mapping between Teichmuller spaces is also understood infinitesimally, and the cotangent action is given by another natural mapping between spaces of quadratic differentials. This one is the push-forward operator, which is some sort of, well, the sum of pullbacks by local inverses. It's formally similar to what people call Rowell operators in various contexts, or in the theory of Riemann surfaces, Poincare series, when you relate when you, for example, take functions on a universal cover and try to average them so that they push down nicely to functions on a quotient. Similar formulas. Okay, and then here's somehow the key diagram that gives the construction after you check things, right? So if you want to remember, I was saying that I'm trying to describe this as some sort of, this discussion as some sort of behind-the-scenes substitute for surgery, or some infinitesimal version of surgery. So you sort of imagine, you say, imagine if I actually wanted to build a deformation of my map by just somehow varying the complex structures on these two surfaces, or these two configurations, the two configuration spaces, the A points, which are in the domain, and the B points, which are in the range. Now I could imagine varying these separately, but then I'd like to be able to fit them together again and interpret the result as a dynamical system. So in particular, if there are relations among the A points, certain cross ratios that should have been preserved, then I should only look at the deformations on the B side which are compatible with them. Okay, so and that maybe sounds a little bit hard to motivate. In the case of these transcendental maps, which was actually the original case I was working with, this is a lot easier to motivate in the following way. So suppose at time 0, I have some dynamical system which is say defined here. And now I want to vary this dynamical system in some sort of I don't know, maximal way. Now, when I say variation, I don't just mean quasi-conformal conjugation. That's too restrictive, because I'd like to be able to do things like break parabolic points, for example, change non-indifferent multipliers into attracting multipliers. Right. So what I really mean is deforming the domain, deforming the complex structure of the domain, deforming the complex structure in the codomain, and then seeking cases where these two are compatible. Right? So it's the difference between having a Beltrami differential which is invariant versus a Beltrami differential which is invariant up to a suitable isotopy. Okay, so what you'd find if you start specifying some complex change of structure, thinking of this now as the range, right? So that's the Beltrami differential which I would indicate in red. Then in the domain, so I'm just going to draw another copy of this configuration now in the domain, but now focus on the domain. So if I have a Beltrami differential mu supported here, and I have the Beltrami differential f pullback of mu extended by 0 supported over here. Now it's almost surely not going to be the case that these agree, right? But they might or might not agree up to the appropriate isotopy. Where the isotopy data, this is isotopy rel. I mean, it's the isotopy data that's implicit in the formulation of these Teichmuller spaces. In effective terms, it means the following. Suppose I want to actually parameterize the variations of the range by the Teichmuller space of that Riemann surface, possibly punctured, and somehow induce a family of maps. Then a bare minimum requirement should be that the induced deformation on the domain is such that the new Riemann surface, the new domain Riemann surface, and the new range Riemann surface are at least conformally isomorphic. They should fit together. And it's quite easy to make examples to show when this might be violated. You could, for example, be doing something that pinches a curve here and has no effect here. So there's non-trivial analytic conditions involved in getting the compatibility of domain and range. Now, it's the same conditions I'm going to be using in the case of rational maps on the Riemann sphere, but it's somehow a little bit easier to miss those at first sight, because after all, by the uniformization theorem, the Riemann sphere is the only genus 0 Riemann surface. And all this compatibility I'm talking about is really an issue of which cross ratios and which others are preserved coherently. Okay, so when all that is said and done, with all that motivation, we see the following. We have these two Teichmuller spaces, Teichmuller space of, say, of X, let's say the Riemann sphere, marked at some set B, mapping in two different ways you prove that they're different, in fact, but there's no reason that they should be the same. So you have one construction which just forgets the extra points from B and doesn't involve this map at all, and there's the other construction that involves the pullback construction. And each of those, for either of those to be defined, there's some condition relating the sets A and B. And if you impose both conditions simultaneously, then both of these maps are defined, and then you can define this space here, which is the locus in Teichmuller space where those two maps are equal. Okay, and this is what I'll call the deformation space. Now, it's not 100% clear from this definition why I should be calling it the deformation space. It's an interesting enough space you could define, but to interpret as a deformation space, what you should then do is go back and take seriously this heuristic I had here that we're trying to actually cook up out of an abstract construction here some universal, some appropriately universal, that's just a heuristic at the moment, family of new maps. So I should show you in principle how to build these new maps, and I kind of did in a hand-wavy way here. If I have a point in Teichmuller space tau represented by a Beltrami differential, I would deform the configuration in the codomain. Then I would take the pullback of that Beltrami differential and define the deformation in the domain. And the fact that A is a subset of B tells me that certain points over here are supposed to be identified with certain points over here, and moreover the ambient Riemann surfaces fit. And that's enough normalizing data so that you can actually write down a new map. And furthermore, you can show that any of the choices that you've made are inessential. So you actually get a family of maps parameterized by this Teichmüller space, and this is somehow the maximal such family, or at least we should formulate and prove that. Okay, so as I said, there's some justification in calling this a deformation space. Now, what properties of this would we like to know? Or what things do we know a priori? So this depends on what you know a priori about these maps P and sigma. But these are familiar characters in Teichmüller theory, and it's known, long time, from first principles, that both of these procedures here, this forgetful procedure and this pullback procedure, define analytic maps between Teichmüller spaces. So the locus where two analytic maps are equal, this can't be that bad. This is an analytic set. Okay, so they say morally it should be a smooth manifold, but maybe there might be singularities. Morally, we should be able to compute the dimension of this manifold by counting constraints, but of course we should verify these constraints are independent, infinitesimally independent. That's the transversality assertion, or at least the first transversality assertion that you need to establish. Okay, so here's the claim, which is that these deformation spaces are in fact complex analytic manifolds of the expected dimension. Okay, and there's a special case to throw out, as always. All this verbiage here, it's much simpler if you're just working with rational maps. You just say exclude Mobius transformations and flexible Lattez examples. You're just enumerating other trivial cases that come about when you allow more generality here. All right, so the proof of this is sort of embarrassingly easy. I mean, once you write all this down, the trick for this theory is to somehow avoid, at every stage, avoid the temptation to write things down in coordinates, because that will only confuse you and give you more work, right? And somehow there's a coordinate-free description of all of these that reveals the only important consideration, which is that the cotangent space is given in terms of quadratic differentials of finite total mass. And so you can use the mass of that quadratic differential and the way it behaves under this push-forward operator to prove the essential statement. It's just some statement about quadratic differentials, some injectivity statement of the operator identity minus f push forward. But because quadratic differentials have this functorial interpretation as covectors to Teichmüller space, it immediately implies precisely the transversality assertion claimed about the deformation space by invoking the implicit function theorem. Okay, so all that needs to be proved is this, and then we apply undergraduate calculus. Okay, now how do we prove this? Essentially, we just go back and we realize that this was already proved in 2 or 3 lines in any individual presentation of Thurston's theorem, and we're even using an easier part of it. We're assuming, in fact, that we actually, well, this can be extracted from what is done in Thurston, Duoddy, Hubbard, but it's actually, in fact, easier. We're just trying to prove that F push forward Q is not equal to Q. The first thing we do is step back and say, well, that would imply that the norm of F push forward Q, the total mass, is equal to the norm of Q. And that's already an incredibly strong statement in and of itself, because it's saying that there's no mass that cancels, you know, that the triangle inequality somewhere is an equality, and that implies an algebraic condition of symmetry, which more or less immediately via Riemann-Hurwitz implies the desired injectivity. And then if you're asking, well, what about this extra generality here? The extra generality only makes it easier. Then you don't have to actually make that last statement about Riemann-Hurwitz, right? In any situation beyond the rational one, the degree is infinite. And so by the time you get to a statement like this, it's already game over. Right, so this observation has been used, for example, in the work of Schleicher, Shishikar, and Hubbard, where they study a version of Thurston's theorem in the exponential family. And there too, somehow this part ends up being just easier because it's transcendental. Okay, so I have nothing to say about global properties, right? From my point of view, global properties of these deformation spaces are intimately connected with what I consider the hard part of Thurston's theorem, namely the global part, the one that actually involves estimates and hyperbolic geometry. But at the same time, what this means is that people who actually understand how to do things like that may actually have some hope of proving things here. My feeling, I don't know if I would even conjecture it officially, but my feeling would be, my desire would be that these spaces are contractible. Because if they are, or at least simply connected, because if they are, then you might be able to make honest sense of this statement about universal families that I'm kind of hedging about. And there may be some progress on this by, well, there's an interesting approach that Nikita just mentioned to me the other day that he and Jeremy Kahn and Tanya Fursova are pursuing. Anyway, I mean, there are things that are done and things that aren't done, but one can, for example, consider the variational theory of other quantities in the setting here, 5-line maps, P and sigma, between this Teichmüller space and this one. And I'm obsessing myself over the locus where these two are equal, but and then taking derivatives to see whether that's smooth or not, but something that completely escaped me to try to play with, which is very nice, is that you could just look at the following quantity. So in this space here, you have this natural Teichmüller distance, and you could look at the Teichmüller distance between these points. So if, on the one hand, if you're interested in when these two quantities are equal, that is when they have zero Teichmüller distance, perhaps you should consider the situations when they have positive Teichmüller distance, and consider the variational theory of that. So there's a very, very simple one-line argument that is essentially the same as the consideration I just mentioned here that proves, again, accepting the obvious exceptional cases, that away from the locus where this function is zero, this function tau goes to Teichmüller distance, which is a real-valued smooth function, that this has a non-zero derivative. That d of this function is not zero. Okay, so that's a very, very interesting observation, which might yet lead to some knowledge on such questions. Okay, I'm running out of time here, so maybe, okay, so this is what I was saying in the beginning. This is still stated in a suitably vague way, but it's less vague because I've specified the spaces involved, and the definitions of these deformation spaces are such that one can actually make explicit sense of this. All of the points that need to be marked to make sense of these are in fact marked. If I'm interested in whether or not a given singular orbit relation breaks, well, I mean, you have to ask what are the A and the B here. For a given, depending on what I want to prove, I have to go out and choose my A and B. And there's a little bit of not art, but craft in this, right? I mean, when you go through and prove various applications, you start to see that to talk about breaking singular orbit relations, you should be choosing your A and B in such a way that one of these has all the relations manifest, and the other has erased some of the relations, right? And then going from A to B is a matter of imposing some additional relations. You could also look at several different relations at the same time. You could have an A1 and an A2 and a B, and see how those interact. And if you want to study variations of multipliers, then those cycles should be there, present in the A and the B. You'd like your cycle to be something that you're explicitly following, so that the variational theory itself, in a coordinate-free way, gives you a recipe for writing down the variation. Right? So to avoid having to actually write it down explicitly, you just build in all the marking in the construction of the space. So in a way, this pushes some of the difficulties. You might think that I'm just hiding the difficulties because instead of proving transversality in the actual space that we all care about, I'm making up my own space that maybe well is designed for things to be transverse. And that's sort of true. Okay, but I redeem myself by saying I look at not just one of these, but all of these, right? There are the conditions on admissible pairs A and B, and you really look at not just one of these spaces, but all of them and the tautological relations between them, and also the tautological relations between these deformation spaces and the space of rational maps. So I'm sort of cutting through some of the transversality stuff right now to show you how you can descend down to earth here. This is what I said already in the abstract here about making compatible deformations in the source and target. And it takes a slightly more concrete form if you're on the Riemann sphere. So this is for rational maps now. It's a familiar diagram that absolutely everybody doing anything with Thurston's theorem draws this diagram with slightly different interpretations of which arrows they care more about. So if I start with a rational map and I have an appropriate pair A and B and I build the deformation space, it really is a deformation space in the sense that this construction here will yield me family of rational maps parameterized by that space, which suitably preserves the data implicit in the marking AB. Well, the data in the marking A, I guess I should say. And what is the relation between these deformation spaces and the space of rational maps, the modular space of rational maps? So, of course, in any given case, you could try to write it down in coordinates, but I prefer avoiding writing it down in coordinates. It turns out that the relation between these is essentially just, well, let's put this way, the derivative of the tautological relation between, the derivative of the relation between these is some tautological map, which the cohomology theory just hands to you whether you're looking for it or not. Right? I mean, if you have, there's just a little bit of general nonsense here, but there's some implied sheaves. There's a short exact sequence of sheaves. Right? There's the sheaf of vector fields. Vector fields are requiring zeros and so forth. And a short exact sequence of sheaves induces a long exact sequence of cohomology groups. Right? When I go from an H0 to an H1, that's when something interesting has happened here. Some global obstruction is being discussed. And the theory, whether you're looking for it or not, the theory hands you a little diagram like this, where the kernel up here can be canonically identified as the tangent space of the deformation space. And the co-kernel down here can be canonically, well, is, concretely actually, is the cotangent space of the moduli space. I'm ignoring orbifold points in this discussion. There's a better way to say it if you have maps with symmetries. But this diagram is just there. And these maps here are just there. These are canonical inclusion and pullback maps between appropriate zeroth and first cohomology groups, just coming from a particular short exact sequence of morphism of short exact sequences of sheaves. And then by the snake lemma in homological algebra, which is also just there, right, there's an induced arrow from here to here. And then you just go back and you check, and just miracle of miracles, that arrow is, in fact, the derivative of what you want. So you can basically, this way, talk your way out of ever making any reference to coordinates at all, and do all of your deformation theory that you like, deformations of multipliers, deformations of parabolic data, and so on and so forth, in the deformation space. And then if you want to see whether or not those transversality results there transfer to here, you just have to check that this induced map here is non-singular, and that's checkable in terms of this diagram, or it's checkable often enough in terms of this diagram. Okay, now what's the virtue of that is that if I do my deformation theory here, then there are coordinate-free descriptions of all of these things I want to vary. I've got to close up now, so I won't actually even say it, but there's a uniform recipe for handling these 3 or 4 different things. One, breaking critical orbit relations, the variation of multipliers, the variation of parabolic data, and even if you push the idea more, the variation of the breaking of Hermann rings. And there's a way of writing things down that these all have the same description in terms of singular parts of appropriate quadratic differentials, and various tautological diagrams and things you get by hitting them with the snake lemma. Right, so speaking here, I have the space of all meromorphic quadratic differentials. Here I have quadratic differentials allowing simple poles, and here I have the quotient space. So this would be some formal direct sum of all greater than -1 polar parts over all points. And then vertically here is some arrow where all the dynamics is hiding. This is identity minus f pushed forward. You have a diagram like this, and the snake lemma gives you a map from the kernel to the co-kernel. That's the interesting map in any setting like that. That's this map. The map from the divergences is a map from the invariant divergences to the, in fact, cotangent space of the appropriate Teichmüller space. Right? If I marked with an A and a B here, I would see this as the cotangent space. Which cotangent space? Well, okay, it's the dual. This is, it would be in the dual of this. Here I have the tangent space. So, this space down here with suitable A and B is the dual of that space there. This map here, so what can we learn about this map? Well, it turns out that this map is often injective. It can't be injective always because one of these things, this has infinite dimension, and this, if I give it any sensible marking, has finite dimension. So there's a huge kernel, right? But there's a nice little argument which is basically, again, the contraction argument in Thurston rigidity, with a little bit extra, which is to allow yourself higher order poles where the, in other words, places where the mass can become locally infinite. And then you have to be careful what you mean by contraction, because the total mass before and after might still be infinite. But if you make appropriate cutoffs, you can make a sensible statement about whether there's more. So there might be some contraction going on here, which might be obscured by some mass production coming out from a repelling cycle here. But so long as that's balanced by even more mass destruction and some attracting cycle here, we can still run the wonderful Thurston rigidity argument. And in fact, if you assume that all of this happens at non-repelling cycles, then there's nothing to be compensated. Right? So everything just works, and in those cases you get injectivity. So if you sit down and look at exactly which conditions you put down on quadratic differentials and count dimensions, you immediately get, well, what you get is that if you restrict to the appropriate space, so, well, there it is. So in this diagram here, this has infinite dimensions and this is finite dimensional, but if I severely restrict where I allow my higher order poles to non-repelling cycles, and only the types of higher order poles that are going to be compatible with that argument I gave, then you can in fact prove by the argument I just gave. The argument I just outlined proves that that restriction is injective. And then this has known dimension here, which is essentially just the number of points in B minus A, for whatever appropriate choice I had. And that means that this space here, with the appropriate subspace there, has to have dimension bounded by that. And then you contemplate what that means, it becomes precisely the following improvement of the Fatouche-Shakur inequality, which counts the number of non-repelling cycles in terms of the number of forward infinite tails of singular orbits. Basically, you recover Shakur's statement with a slight improvement, because if your parabolic points, so at your parabolic points you can consider the holomorphic index, and having being or not being, having that index being in one of these special half planes or not, can give you an extra weight in that count. Okay, so somehow the, thinking of a fancy word this morning to describe this. So you have this Fatouche-Shakur inequality and this injectivity statement that you get here on the appropriate subset is some sort of categorification of that. You're showing that two natural numbers satisfy a particular inequality because they happen to be the dimensions of two linear spaces which are related in some sort of tautological injective way. And furthermore, that statement in fact has an integrated form, and it in fact is this, or the various consequences of that statement when you integrate. In other words, when you apply the inverse function theorem, you can just go through, and there's a dictionary between various quadratic differentials and various quantities whose variation you might want to prove is non-zero in some combination or another, and you thereby get these transversality statements. Okay, so I want to close. To actually get any consequences in practice, right? I mean, you do have to make sure that whatever family you're working in is such that the transversality here, which typically gets inherited here, isn't somehow messed up by a poor coordinate choice, right? You could, just to make a stupid example, we all know the work in this family here, but there are various transversality statements about this family here which I could violate by working in this family here. Okay, so if it's polynomial families, if it's things that enough people have written papers on that they're accepted normal forms, it's sort of understood sociologically which families we work in and which families we don't work in. But if you're looking for a principled description of which families are somehow natural families, I claim that this discussion here involving the deformation space and this diagram somehow puts you in the right frame for that. That really, you should be doing your calculations in the deformation space. That's where the transversality conditions can be most transparently specified and most transparently proved. And then, the follow-up step, you apply that theory to your discussion. Maybe this is where the actual choice of coordinates of normal forms becomes relevant. You do some calculation to make sure that you haven't somehow accidentally done this somehow. And then that's it. Okay, so I should finish now. So thank you.
Are there some questions for the speaker?
Yes.
I have a little question.
Yes.
When you discussed paradigms, you mentioned the condition of Brunner rotation numbers.
Yes.
How does this rotation number come into play?
Right. Okay. So that's a whole other talk, right? But no, but I can say it in a nutshell. Okay. So there's a lot more. Okay. So this dictionary with divergences here, basically somehow all the singularities I'm talking about are things that you observe concentrated along at a point or maybe along a periodic cycle. And you can somehow, even if you don't start out doing this, you can find them all algebraically by just playing around and doing a calculation for fun. Okay, when you want to vary Hermann rings, you have to figure out what sort of singularity is involved. And this is a little bit more subtle because the singularity is distributed. And there's two slightly different descriptions of this. I think probably both are relevant. But one description is that it's a piecewise meromorphic quadratic differential with allowed jump discontinuities along four curves of Hermann rings, where the jump discontinuities are some constant times the invariant quadratic differential there. Another way of describing this, which is probably better, which is due to Xavier, is again in terms of cohomology, appropriate one cocycle. Now, that's somehow the local picture of what you would do, and then you somehow want to assemble local deformations into a global deformation. Now, there's a local statement. For example, suppose I just have a germ with a given multiplier, and I want to perturb the multiplier. Well, in principle, there's something to prove there, but you prove it by writing down 1 plus epsilon times the multiplier, and you're done. So nobody ever has to think about that part. But that corresponding local behavior, what do the linear models look like? That's already a non-trivial theorem. That's the thesis of Rissler. So the thesis of Rissler says that if you start with a rotation, and then an actual rotation of a circle, and then you consider a family, maybe a real analytic rotation, you consider a family of these, what can you say about the rotation number? Does it, quote unquote, have non-zero derivative? Okay, well that doesn't even make sense, but you could make sense of some consequences of that in terms of the change of rotation number or not. And that's just the local theory. You then have to somehow glue the local theory to the global theory, and that's going to involve linearization, and that's where the Brunner condition comes in.
Okay.
Okay, some more questions.
Yeah, just to have a particular example of how it works, could you please show the triple FAB, which the the moduli space associated with the deformation space is the picture that you've shown.
Okay.
So the parabolic,
you mean show you and if, I mean, okay, so this of course is actually in this picture I have here?
yes.
Okay, so this is the actual algebraic parameter space, so I have to choose an A and a B. So I'm not claiming that this is the deformation space. Here, let me tell you what.
No, this is not a deformation space, but it's associated with some deformation space.
It's associated to many. It's associated to many deformation spaces. In fact, each map in here, and each admissible marking gives a deformation space, and those deformation spaces suitably map onto. Let me answer in a slightly different case. That will probably help you more. Let's look at the quadratic polynomial family. Okay, here's an actual case of this. This somehow trivializes things, but it trivializes things in a useful way, I think. So here's the quadratic family. It's parameterized by a complex plane. And suppose, let's see, I want to take, how do I think about it? Let's see, suppose I want to take, suppose I'm interested in quadratic rational maps whose forward critical grid begins like this, where it begins like this means that these 3 points are distinct, without any commitment to whether this next point is or is not this point here. Okay, so let's pick a point where they actually are distinct. And let's call this, okay, technically I'd rather start at the critical value and go one later, but it's a matter of taste. Since I'm drawing it this way, let's just do it this way. So I can say that this is B. Hold on, you know something, I think just to be sure, just to be absolutely sure, I think I want to do, now let me finish, all right, so this is B, 1, 2, 3, 4, and this would be my A, and I'm going to restrict it, so when in fact is this an honest choice of things? Well, when these 4 points in fact are different, so I should be excluding various centers. Do I do this, or do I have 3 points here? At the end of the day, I should be excluding these points here, and perhaps the Miserevich points. Okay, now, because A has only 3 points, okay, the Teichmüller space marked at A is in fact a 1-point space. So this is the one situation we can actually calculate anything explicitly. If I have 2 maps in the Teichmüller space of X marked at B, right, this is there are 4 points here. Okay, so this is, if you like, this is the upper half plane. Okay, so one-dimensional complex manifold. And I have these 2 maps to this 1-point space. There's a 1-point space, so these have to be the same map. So the deformation space in this case is actually everything. And so the deformation space just is this Teichmüller space, and the relation between this deformation space and the parameter space is just the fact that the Teichmüller space of X marked at B is the universal cover of the moduli space of X marked at B. And if I just remove the points which should be suppressed, sort of implicit in this description here, which one should be suppressed, then that's what it is. But in a way, this is sort of trivial. I don't think you actually learn anything from this description, but it sort of indicates what it is. Now, more generally, if you have something like a pure N0 curve, right? If you have an appropriate mark, let's suppose that you're interested in preserving the fact that one of your critical points has period N, and the other is allowed to do whatever you like. So if I were going to set up some deformation problem for this, I would take as my B the whole critical cycle here, and some initial segment of the orbit of the other critical point, and then as my A, I would take the whole cycle here and one shorter initial segment there. And I would get a one-dimensional deformation space by this theory, and this deformation space will tautologically map onto, well, I don't know, well, it's tautologically map to, let me be careful here, well, tautologically map to the appropriate PRN curve, precisely because things are set up so that this particular relation here, that one critical point has that period, this has been preserved Okay, so you can't help but map to that curve. Now, the mapping to that curve,
But then,
Yeah.
then you get power K0, rather than, then you get power K0 rather than power K.
well, yeah, so if you want peer 1, okay, so, but this, okay, well, but this isn't for 0. Okay, so for here, the point is there's no one choice. Okay, so maybe I should see here that if I take a map here, the deformation space of a map here is going to actually be, okay, I mean, having this multiplier is not something you can state in terms of the critical orbit relations. So in fact, this will be this is better understood as the image of some locus in the deformation space. Namely, it's the locus where a certain multiplier function that you can consider remains constant. So what I would do is, if I already know I'm interested in a fixed point of that multiplier, I would mark that fixed point, and then mark however much of my 2 critical orbits I need to have the minimum number of points I need to describe everything. Maybe call this A, and this B, and I get my space def AB, which basically is canonically isomorphic to def AB for almost any other quadratic rational map, with or without this prescribed multiplier. But then, within that deformation space, I pose the question, what is the locus where this multiplier does not change? And then that will be some smooth, one-dimensional thing which suitably maps to this.
Some more questions. So if not, let's send the speaker again.